All right, today on this lesson is lesson 25. It's in two parts. We'll talk about two different types of network problems for our first part one. And then part two, we'll talk about another network application. And these applications will be the last applications of linear programming that we'll talk about, but hopefully you can appreciate the breadth and the types of problems that you can address with linear programming. So let's go ahead and dive in. Now, I will say, first of all, none of this that I'm going to show is in the textbook. So these are all it's not original, but there's not anything in the textbook to support this. So you'll want to go over these videos and look at the Excel spreadsheets carefully. But our two problems that we're going to talk about in this part of the lesson are, first of all, is the minimum spanning tree problem. And then the next one that we're going to talk about is the shortest root problem. Now, some students will have a tendency to get these two confused, but they are quite similar, but they have different objectives, and certainly we'll talk about that as we go forward. All right. So first, the minimum spanning tree problem, and the minimum spanning tree problem is going to use what we're going to call is, and we'll see on the next slide, we'll call it the greedy algorithm. First of all, let me orient you on what the information here is on the screen. First of all, we've got a network, and that network has 7 different locations. 1, 2, the origin, which is O, the terminal or destination T, and then 5 intermediate locations A, B, C, D, E. And then between each of these locations are pathways. So the pathway that goes from O to A, and it has a length of 2. So 2 miles, costs $2, 2 minutes, 200 yards. Its length is 2. So the numbers on the paths are the distances between the locations that can be measured in any kind of dimension. And now the particulars of this problem is that let's just hypothetically assume that this is our campus, and location O is plant operations, location T is the Southeast Georgia Conference Center, and then there's various locations in between. Maybe this is the Student Activity Center, the Campus Center, maybe this is Academic Commons North, Academic Commons South, and the library. And for our students with disabilities, we need to make sure, in case of inclement weather, that there is a paved pathway that connects every location to every other location. So it doesn't mean it has to be the most direct way to get from every location to every other location, but it's just possible to get from every location to every other. And so the objective is to determine those paths that interconnect every location with the minimum total distance. So we want to be able to get to any location from any other location along a paved pathway. All right, so let's see how we will solve this problem. And as I mentioned previously, we're going to use the greedy algorithm. And this is the listing of the greedy algorithm. And I'm going to go through the example of how this works. This is the only problem, or the one problem that we're not going to solve with linear programming. We're just going to use this algorithm, and I'm going to go step by step to show you how we do this. So step one. Step one is we select the shortest path, the shortest segment, and connect the two locations. And that can be any of these segments. And you'll notice I'm just going to arbitrarily choose. We've got two ones. We've got a one here and a one here. But I'm going to choose this path B and C, and you could choose any, just the shortest, and break ties arbitrarily. And so we're going to connect path B and C, and it has a length of 1. Okay, so those two locations, those locations are connected, and we've chosen path of length 1. All right, and now we continue that, picking the shortest pathway unless a loop is formed. And then if a loop is formed, choose the next shortest path that doesn't form a loop. So let's continue. The next shortest path, as we saw, is this path of length 1. And so we're going to connect location D with location E, and we're going to use this pathway. All right. The next shortest path, okay, well, are there any more 1s? No, there's no more 1s, but there is a 2. In fact, there are 2 2s, so we could choose either one. So let's just choose this 2. So we're going to connect location A to location O, and we're going to use this path. Then we're going to look at the next path of length 2, which is here, and we're going to connect A to B here, and so that pathway, that pathway is connected. So now, are there any more 2s? There are no more 2s. So then we're looking for paths of length 3, and there is one. Here's one of length 3. And we're going to connect this location to this location. Now we're going to see if there's any paths of length 4. And there are. There's one here, and there's one here. So let's arbitrarily say we're going to pick this location here. But if we do that, you'll notice there's a loop formed, because if we connect this with this along path of length 4, there's a loop in here. That would create a loop among those 3 locations. So we definitely don't want to use this length of 4. So what about the next length of 4? Hopefully you can see that if we connect this path of length 4, then there's going to be a loop here. And so we don't want to do this. We won't use this path. So then we go to length 5. All right, so let's look for length 5. There's 2 of length 5. There's one here and one here. If we pick the first length 5 here, then there will be a loop in this area. So we're not going to be able to use this 5, but let's see what happens if we pick this 5. In fact, yes, because there we can connect this location along this path to T, and we've connected all locations, so now we can stop. Okay. So now what I want you to see is along the blue paths, you can get from every location to every other location. In other words, you can get from the origin down to location C, We can get from our origin to location C along a path, along a paved path. So we would have to go up to A, then to B, and then to C. Clearly, that's 2, 4, 5. That length is 5 to go like along those 3, which is longer than 4. But you definitely can get there along the pathway. And in fact, you can get to every other location along a paved pathway. It might not be the most direct, but it is, you can get to every location from every other location. And you'll notice now that there's 2 things I want you to notice. Number 1, the length of this tree is, we took a pathway of length 1, we took 2 of length 1, we took 2 of length 2, we took 1 of length 3, and we took 1 of length 5, and that adds up to 1, 2, 6, 9, and 5 is 14. So its length is 14. The other thing that I want you to notice is how many paths were used. And we used, of these, we used pathways 1, 2, 3, 4, 5, 6. And there is a rule for a minimum spanning tree problem. For any minimum spanning tree that has any number of nodes, for example, let's suppose we have a path that has n locations. N is the number of locations. Then in every case, we'll have n minus 1 as the number of paths in the tree. Okay. And this is a theorem for this type of problem, and this is how you'd solve the minimum spanning tree problem. But again, the idea is how do you connect every location, not in the shortest way overall from each location, but how do you connect every location with every other location in the shortest way possible. Okay, that's the minimum spanning tree problem. The next problem is the shortest route problem. Again, it looks very similar and it sounds very similar because we're talking about the shortest route. But in this problem, we're going to designate our starting point here at the origin. We're going to designate our finishing point here at a destination. And what we want to do is to travel through the network from the origin to the terminal by taking the shortest path through the network. And what you'll need to remember here is we do not need to pass through every location. Just get from O to T as quickly as possible. So that's the key thing. We do not need to pass through every location, or we do not need to connect every location. All right. And this we are going to solve with our linear programming. We are going to use linear programming. All right. The numbers are the distances, between each location. And again, they can be any measure of distance, cost, or time. So that's we're going to try to find how can we most quickly get from this to this location. And again, this is what your Google Maps, what your GPS, similarly to how those paths, software apps, those apps work for you. Okay, so now let's see how this works. The first thing that we're going to do is we're going to convert every path to either a one-way path, such as from O to B, or a two-way path. In other words, we may be able to pass from C to E, or we may be able to pass from E to C. And hopefully you can see, essentially you would want to create every pathway. In other words, these are showing that there, if you will, two-way streets between these locations. The reason that the origin to each one of its destinations is only one direction is because if you ever leave the origin, you're not ever going to want to come back to the origin. Similarly, going anything into the destination or to the terminal, once you get to the terminal, you're done, and you'll never leave the terminal. So hopefully, now we're going to use linear programming, and hopefully what you can see now and visualize is this is exactly the same structure as our transshipment problem. Is exactly the same structure. And so hopefully hopefully you'll be able to determine quickly how many decision variables we have and how many constraints we have. It's going to turn out that there are three. There are going to be 3, 4, 5, and then there's 2, 4, 6, 8, 10, 12, 14. There's a total of 19 different decision variables. And hopefully you can see also that there's going to be 1, 2, 3, 4, 5, 6, 7 constraints, not counting non-negativity. All right. So hopefully you can already in your mind begin to see how we're going to formulate this problem. All right. So let's start to work through that. The next slide, we're going to talk about the decision variables. In fact, we already know that we're going to have 19 decision variables, but we define those decision variables. And I'm going to define those. I'm going to let, for example, with an example, I'm going to start O to A. O to A is I'm going to put the number of times path from O to A is used. I'm giving this definition for a reason. All right, and so in general, we're going to say IJ is the number of times at the path from I to J is used. And we're going to see that in this case, I can be everything in the set from O, A, B, C, D, E. It can't be T because you're never going to leave, excuse me, our terminal, because you're never going to leave the terminal. And then J is going to be to set everything but the origin. So A, B, C, D, E, and terminal. So those are our decision variables and our definitions. All right, so now we're going to look at our objective function. Now you'll notice that each one of these decision variables has an associated distance with it. And just like before, we're going to, and again, hopefully, this is the, let me to remind you, this is the shortest path problem. So that in your mind should indicate what type of objective function it is. If we're trying to choose something that's the shortest, this is going to correspond, hopefully you'll see, it's going to be a minimization. It's going to be a minimization problem. And in fact, it is going to be. And so you should ask yourself, how many terms is this objective function going to have? And hope, again, it's the exact same format you're going to see. It has 19 different terms in this objective function. So let's start to look at this. So our objective function is going to be minimum, minimize, distance. And so we're gonna want to have minimum distance, minimize our which is distance, which is going to be equal to 2 times that path, if path is how many ever times path O to A is used, plus 5, and then if path O to B is used, and 4 O to C. And then we begin at A plus, I'm just going to do a few of these, 2 times A to B plus 2, not equals, but plus 7 times A to D, and so forth. However, you're going to also notice we have to include 2 times B to A, because BA is different from A to B, and also 7 D to A times D to A, and so on and so forth until we get to the terminal, which we have 5 times DT plus 7 times E to T. And if once everything is included, there's going to be 19 different terms in this objective function. Okay, so hopefully that makes sense. Again, it has exactly the same structure. All right, so now let's look at our constraints. And we already talked about our constraints because we know we have 7 constraints, one for each of our locations. Location O, A, B, C, D, all the way to T. And as you hopefully you've seen now that we've got these locations, A, B, C, D, and E. These are equivalent to our transshipment point. Let let me erase this and start over, that in fact, A, B, C, D, E, these are our transshipment nodes, locations. And you might already anticipate O is our origin, or is where we start our supply, and T is our terminal, or is where we have demand. And so, as before, we have supply constraints with respect to the origin. We have a single demand constraint with respect to the terminal, or the destination, and then we have 5 transshipment locations where whatever goes in is going to equal to whatever comes out. And we're going to use our graph. We're going to use our graph to help us build these transshipment constraints. So let's start. Let's start with our origin. And how are we going to do that? The one thing that I haven't really addressed yet is the following. What's our demand? Excuse me. What's our supply at the origin, and what's our demand at the terminal? Hopefully, with respect to how we define the decision variable, it'll help you infer what that demand is, because we want to get from the origin to the destination one time in the shortest way possible. And we're going to use these paths no more than once. So in essence, our supply at the origin is 1, and our demand at the destination is 1. We start with one person, one truck that leaves the origin, and that person has to get to the destination. Exactly 1 leaving and exactly 1 arriving. And so for our origin, the supply node, or the supply constraint, is going to be OA, not 1, OA plus OB plus OC is going to equal to exactly 1. And that's our supply constraint. Our demand constraint, and hopefully you're ahead of me, on this end is D to T plus E to T equals exactly 1. And now we have our 5 locations in the middle. And so these are going to be our transshipment. Everything that goes in, whatever goes in has to equal to whatever goes out. That's going to help us build. Now let's look at A. Let's look at location A. And what I'm going to do is I'm going to do these just for a couple. I'm going to do this for A and B, and then I'm going to leave it to you to confirm C, D, and E. So let's look at A. Let's just look at A. And we use our diagram to help us. You'll notice we have 3 paths coming into A. Those are the ones with the arrow. So there's a path coming into A. Here's another path coming into A. And here's another path coming into A. And there's two that are leaving A. And that's the one that goes from A to D. And that's the one that goes from A to B. So that's how we're going to help us know what's going in to A and out of A. So for A, what's going in? O to A, B to A, and B to A. Look, not equals plus B to A. That's what's going in. Now that equals to what's going out, or what's going out, where we're going from A to B, and the only other one is we're going from A to D. That's our balance constraint at location A. Now it's going to be more. Let's look at B. B is probably the most complex one. So let's just look at B, and hopefully you can see there's 1, 2, 3, 4, 5 paths coming into B. So let's tackle those first. So what's coming into B? O to B, coming from the origin to B, plus A to B, plus C to B, plus D to B, plus E to B. And I think you can confirm that's O to B coming in, A to B coming in, C to B coming in, D to B coming in, and E to B coming in. And so what's going out, that's going to equal to what's leaving B. Well, we go B to A, we go B to C, go B to D, oops, go B to E. So this is the balance constraint for location B. Again, I'm going to leave it to you to complete that. And I would like for you to try that, to complete that on your own. Make sure you can understand for both, for C, D, and E. Now that completes the formulation. And the next slide is going to show you the complete formulation. Again, we've got a supply is 1, our demand is 1, IJ is the number of walkers or number of times that are using the path from I to J. Where our objective function is, as we've already said, is the minimization problem. Our supply is 1, demand is 1. We don't want to forget non-negativity. And the balance constraints, these are all of the balance constraints. So this is the complete formulation. Now, in the next video, I'm going to go through and show you this Excel solution to this problem. And when we get through, you're going to see this is going to be that you can come back and look at this, but this will correspond to the Excel solution. This is the solver window. Again, I want you to be sure to realize that this is a minimization problem. And there's two sets of constraints, and they're equal. You can see they're equality constraints. The first set is going to be our supply and demand, and the second group of these is going to be the balance constraints. And then always we want to make our variables non-negative. Select simplex, and then click solve, and you'll be able to see how this works. The last slide I want to talk about is the following: is the difference between those two, and we'll see this solution when we look at Excel. We've already looked at the minimum spanning tree solution, and we saw that the minimum distance to interconnect all of the nodes was 14 units. And we'll see on the next, when we solve this in Excel, that the shortest path from the origin to the destination is along this route, and it takes 13 units. And so, and you'll notice, as said before, we do not have to connect. We don't have to go through this location. For the minimum spanning tree, we do have to connect every location, but we do not have to connect. We don't have to go through. We just need to take the shortest path. It might have been too that the shortest path might have gone from B to D, and so we might not need to go to E either. But that's the way the problem works out. You can see that from B to D is 3, from E to D is 1, and so getting from here from B to D is only 4 units long rather than the 5, and so that's why the path goes this way. So anyway, let's the next video we'll look at the Excel solution.